Hello, my name is Julia Stoyanovich, and today I have the honor and the pleasure to share with you some of my thoughts on responsible data management. AI is great. The convergence of unprecedented data collection capabilities, enormous computational power, and broad acceptance of data collection and analysis as a way to move society forward is offering us tremendous opportunities to do good. We can accelerate scientific discovery in areas ranging from astrophysics to medicine. We can boost innovation in a myriad of ways, from self-driving cars to advertisement targeting and back. We can improve society by improving how governments function, by helping make resource distribution more equitable, and by bringing greater transparency and accountability to government operations. And perhaps most importantly, we can get AI to do all of our work, so we can just relax at the beach. To make our discussion concrete, let us focus on automated hiring systems. A recent report from Upturn describes the hiring process as a series of decisions that form a funnel. Employers start by sourcing candidates, attracting potential candidates to apply for open positions through advertisements, job postings, and individual outreach. Next, during the screening stage, employers assess candidates, both before and after those candidates apply, by analyzing their experience, skills, and characteristics. Through interviewing applicants, employers continue their assessment in a more direct, individualized fashion. During the selection step, employers make final hiring and compensation determinations. Importantly, data and predictive analytics are used during all of these stages. The hiring funnel is a socio-legal technical system operationalized as a sequence of data-driven, algorithm-assisted steps, in which a series of decisions culminates in job offers to some candidates and rejections to others. As stated by Jenny Yang, former commissioner of the US Equal Employment Opportunity Commission, automated hiring systems act as modern gatekeepers to economic opportunity. And now, some bad news. One of the earliest indications that there is cause for concern came in 2015, with the results of the Ad Fisher study out of Carnegie Mellon. The authors ran an experiment and found that ads for high-paying jobs were shown far more frequently to men than to women. This brings back memories of the time when it was legal to advertise jobs by gender in newspapers. This practice was outlawed in the US in 1964, but it persists in the online ad environment today. Let us advance to the next stage of the hiring pipeline, resume screening. In late 2018, it was reported that Amazon's AI recruiting tool that was developed with the stated goal of increasing workforce diversity in fact did the opposite thing. The system taught itself that male candidates were preferable to female candidates. It penalized resumes that included the word women's, as in women's chess club captain, and downgraded graduates of 2 all-women's colleges. Other examples of discrimination include shutting out people suffering from mental illness, such as depression or bipolar disorder, on the basis of online personality tests, even if they have the right skills for the job. Another example, later yet in the hiring funnel, perhaps during a post-interview background check by a potential employer, was surfaced by Latanya Sweeney, a computer science professor on the faculty at Harvard, who showed that Googling for African-American sounding names like Latanya is more likely to trigger ads suggestive of a criminal record than with white-sounding names like Kristen, even when controlling for whether an individual in fact has a criminal record. To summarize, despite their potential to improve efficiency for both employers and job applicants, automated hiring tools are also raising concerns. These pertain, broadly speaking, to the unfairness in the decisions made by these systems. We denote this by discrimination, or in the process by which these decisions are made. These are due process concerns. Very often, discrimination and due process violations are linked to the term bias, a term we will revisit throughout the talk today. There are also concerns about whether these tools actually work, whether they are picking up useful signal from the data or are an elaborate coin flip at best. As Arvind Narayanan puts it, are these tools AI snake oil? In the complex ecosystem in which automated hiring tools are commissioned, developed, and used, we must ask ourselves, who is responsible for ensuring that these tools are built and used appropriately? Who is responsible for catching and mitigating discrimination and due process violations, and for controlling the proliferation of snake oil under the fancy label of data science and AI? In response to the question about responsibility, there has been much activity in putting forth ethical guidelines and frameworks, and in making attempts to regulate the use of data-driven algorithmic tools, such as those that make part of the hiring funnel. This activity is broader in scope than algorithmic hiring, so let us now step back for a more systematic view and discuss automated decision systems, or ADS. The hiring funnel, as well as each component of the funnel, are examples of ADS. These systems process data about people, some of which may be sensitive or proprietary. They help make decisions that are consequential to people's lives and livelihoods. They involve a combination of human and automated decision-making. They are designed with the stated goals of improving efficiency and promoting, or at least not hindering, equitable access to opportunity. And finally, they are subject to auditing for legal compliance and, at least in theory, to public disclosure. ADS may or may not use AI, although many of them are billed as AI, and they may or may not have autonomy, but they all rely heavily on data. This, as I will argue in the remainder of my talk today, puts ADS regulation, design, development, and deployment firmly within the purview of the data management community. How might we go about regulating ADS? And should we even attempt to? While the predominant sentiment in the industry is still that regulation will stifle innovation, industry alone doesn't get to decide. And even in the Silicon Valley, the need for meaningful regulation to make compliance easier and to limit liability is starting to be more and more broadly recognized. There is much debate on a specific regulatory framework. Should we use precautionary principles that can be summarized as better safe than sorry, or more likely attempt a more agile, risk-based method, such as algorithmic impact assessment? All this and more is the subject of intense debate, some of which I had a chance to witness firsthand. New York City, where I live, recently made a very public commitment to opening the black box of the government's use of technology. In May 2018, an Automated Decision Systems, or ADS task force was convened, the first such in the United States, and charged with providing recommendations to New York City's agencies about becoming transparent and accountable in their use of technology. The task force issued its report in November 2019, making a commitment to using ADS where they are beneficial, to promoting fairness, equity, accountability, and transparency in their use, and to reducing potential harm across their life cycle. The first point here reinforces the no to AI snake oil sentiment. Can the principles of the responsible use of ADS be operationalized as a matter of policy? What will it take to instill responsible ADS practices beyond government? And what do we, as members of the technical community, have to contribute? Before diving into research challenges and directions, let us step back and think carefully about the role that technological interventions, such as data management solutions, can play in supporting the responsible use of ADS. This discussion is necessary to help us find a pragmatic middle ground between the harmful extremes of techno-optimism, a belief that technology can single-handedly fix deep-seated societal problems like structural discrimination in hiring, and techno-bashing, a belief that any attempt to operationalize ethics and legal compliance in ADS will amount to fair washing and so should be dismissed outright. To start with the framing, let us recall the concerns about gender, racial, and other types of bias in algorithmic hiring. What's in common between the examples we saw of things going wrong? These all can be seen as there being bias in predictive analytics. But what do we mean by bias? Our meaning of this term is not in the traditional sense that's used by statisticians, who say that a model may be biased if it does not summarize the data correctly. Instead, we are seeing examples of societal bias exhibiting itself in the data. Let's unpack that further. Data is an image of the world, its mirror reflection. When we think about societal bias in the data, we interrogate this reflection. One interpretation of bias in the data is that the reflection is distorted. We may systematically oversample or undersample in particular parts of the world or otherwise distort the readings. Another interpretation, though, is that even if we were able to reflect the world perfectly in the data, it would still be a reflection of the world such as it is, and not necessarily of how it could or should be. I'd like to make 3 important points here. The first is that a reflection cannot know whether it is distorted. Based on the reflection alone, and without knowledge about the properties of the mirror or of the world it reflects, we cannot know whether the reflection is distorted, and if so, for what reason. That is, data alone cannot tell us whether it's a distorted reflection of a perfect world, a perfect reflection of a distorted world, or if these distortions compound. The assumed or externally verified nature of distortions has to be explicitly stated. The second point is that it's up to people, individuals, groups, and society at large, and not up to data or algorithms, to come to consensus about whether the world is how it should or could be, or if it needs to be improved, and if so, how we should go about improving it. The third point is that changing the reflection does not change the world. If the reflection itself is used to make important decisions, and we agree that it is distorted and explicitly state the assumed or verified nature of such distortions, then compensating for the distortions is worthwhile. But the mirror metaphor only takes us so far. We have to work much harder, usually going far beyond technological solutions, to propagate the changes back into the world, not merely brush up the reflection. To illustrate these concepts, I will now describe a recent technical approach for algorithmic fairness and diversity. The focus of this specific work is on set selection and ranking. This approach is one of several methods discussed in the paper that accompanies this talk. Consider the task of selecting 4 candidates among 16 job applicants. Our goals are twofold. The first is diversity. We wish to include 2 candidates of each gender and at least 1 of each race. The second goal is utility, maximizing the sum of scores of the selected candidates, subject to diversity constraints. You can see a list of candidates in the table here along with their scores. For example, candidate A has score 99, that is the top-ranked candidate, and candidate L has score 83. Observe that male candidates have higher scores in my example than do female candidates of the same race, and that whites have higher scores than blacks and than Asians. The highest scoring set of 4 candidates that satisfy the diversity constraints is highlighted in pink. with sum of scores equaling 373. If we consider the selected set more closely, however, we observe a problem. The problem is that we picked the best, according to score, white and male candidates A and B, but we did not pick the best Black, Asian, or female candidates. Note that our example was deliberately constructed to highlight the following. If some population groups have systematically lower scores, then it costs less to skip their best scoring members in the name of diversity. This runs contrary to the nature of the diversity objective, which is to equalize access to opportunity. This also represents unfairness under a particular belief system. Suppose that scores represent effort, for example, how hard someone studied to do well on a test. We may take a relative view of effort and assert that scores are more informative within a group than across groups. Further, we may assert that it is important to reward effort. Taken together, these beliefs correspond to a Luck egalitarian conception of equality of opportunity, denoted here with a rainbow unicorn. But there is something we can do. Consider the set of 4 candidates highlighted in blue. This set still meets the diversity constraints, and its score is lower by 1 than the score of the pink set. This utility loss is inevitable, but it's very small. The blue set contains the top scoring candidates of both genders and the top white and Black candidates, and so is much better in terms of rewarding effort across groups. Having stated our beliefs and observed the trade-off between diversity, utility, and fairness, we are now ready to design an intervention. For example, we may compute unfairness for a particular group, like the female candidates shown here, as the ratio of the score of the lowest scoring selected candidate, that's K with score 83, and the score of the highest scoring skipped candidate, that's D with score 95. We can then reformulate the selection process to balance unfairness across groups. We did this and quite a bit more in the paper, designing several fairness metrics of this sort, both for set selection that I just described and for ranking. We devised an integer linear program to encode all of these constraints, and we ran experiments showing that the utility cost of balancing fairness is low in most cases. For a systematic treatment of fairness in ranking and a mapping to equality of opportunity frameworks like the rainbow unicorn here, please see an upcoming survey that I co-authored with the very talented Maike Zelike and Kay Yang. Let me stop now and take your questions. But before I go, I'd like to share that the graphics used in my talk today are part of Mirror Mirror, the first volume of the Data Responsibly comic series. Mirror Mirror was released today. It was created by the talented Fala Arif Khan. Please share it. You can find it under the hashtag RDSComic on Twitter. Thanks. Welcome back to the second part of our conversation on responsible data management. Welcome back to the second part of our conversation on responsible data management, and specifically on automated decision systems, or ADS for short. One way to conceptualize ADS is simply as predictive analytics that take as input a nice, clean, rectangular dataset, crunch it, and produce a result. If we then notice that the result is such that no women are shown ads for high-paying jobs, or no Black candidates are invited for job interviews, then we have 3 choices. Tweak the input data, for example, upsample or downsample some groups. Tweak the algorithmic box, for example, add a regularization term, or tweak the result, for example, reassign outcomes. However, This view of an ADS is a frog's eye view. We need to expand our scope and also ask what specifically happens inside the box, how results are used, and where the data came from. In other words, we will gain much more power to incorporate ethics and legal compliance into ADS if we see these systems through the lens of the data lifecycle. Responsibility concerns and important decision points arise in data sharing and annotation, acquisition and curation, cleaning, integration, querying, and ranking. We will miss opportunities for improving data quality and representativeness, controlling for bias, and allowing humans to oversee ADS operation and exercise agency over its decisions if we do not consider these earlier lifecycle stages. Because we now take a broader view of ADS, we also need to expand our conception of bias. In their seminal 1996 paper, Friedman and Nissenbaum identified 3 types of bias that can arise in computer systems: pre-existing, technical, and emergent. Pre-existing bias exists independently of an algorithm and has its origins in society. This is the societal bias we've been discussing so far. Technical bias can be introduced at any stage of the ADS lifecycle, and it may exacerbate pre-existing bias. The bad news is that risks of introducing technical bias stemming from data management components abound. The good news is that, unlike with pre-existing bias, there is no ambiguity about whether a technical fix should be attempted. We break it, we fix it. If technical systems we develop are introducing bias, then we should be able to instrument these systems to measure it and understand its cause. It may then be possible to mitigate this bias and to check whether the mitigation was effective. Finally, emergent bias arises in the context of use and may be present if a system was designed with different users in mind or when societal concepts shift over time. In web ranking and recommendation in e-commerce, a prominent example is rich gets richer. Emergent bias arises because searchers tend to trust the systems to indeed show them the most suitable items at the top positions, which in turn shapes a searcher's idea of a satisfactory answer. In all cases, any attempt to fight bias must begin by stating beliefs and assumptions explicitly. With that, I'd like to dive into a discussion of concrete methods to tame technical bias. Consider Anne, a data scientist in the human resources department at a large retailer. Anne was tasked with developing a model that predicts the level of compensation that should be offered to successful job applicants to make sure that they accept the offer. Anne includes candidates' self-reported demographic data together with their employment histories as the input. Following her company's best practices, Anne starts by splitting her dataset into training, validation, and test sets. She then implements data pre-processing, interpolates missing values. After that, she performs model selection, and finally, tuning and validation. Next, Anne considers the accuracy of the trained model and observes a disparity. Accuracy is lower for female applicants. This presents a fairness issue. Considering the complexity of the data processing pipeline and the multitude of objectives that Anne has to juggle, she has a long night of debugging ahead of her. Anne goes back to data pre-processing and follows a hunch. She observes that the value of the attribute age is missing far more frequently for female users than for male users. And this attribute seems to be important for accuracy of this decision. Anne looks at the data imputation method and she compares age distributions by gender and notices differences starting from the mid-30s. Anne revisits the data cleaning step and selects a state-of-the-art data imputation method to fill in age in customer demographics. This intervention that Anne found because she followed a hunch seems to help. Let us extrapolate from Anne's experience and list some other sources of technical bias that may arise during data cleaning due specifically to incorrect modeling assumptions. Consider a form that gives job applicants a binary choice of gender and also allows to leave gender unspecified. Suppose that about half of the users identify as men and half as women, but that women are more likely to omit gender. Then, if mode imputation, that is replacing a missing value with the most frequent value for the feature, is used, then all unspecified gender values that are predominantly for women will be set to male. More generally, multi-class classification for missing value imputation typically only uses the most frequent classes as target variables, leading to a distortion for small population groups, because membership in these groups will never be imputed. Next, suppose that some individuals identify as non-binary. Because the system only supports male, female, and unspecified as options for gender, these individuals will leave gender unspecified. If mode imputation is used, then their gender will be set to male. A more sophisticated imputation method will still use values from the active domain of the feature, setting the missing value of gender to either male or female. This example illustrates that technical bias can arise from an incomplete or incorrect choice of data representation. Finally, consider a form that has home address as a field. A homeless individual will leave this value unspecified, and it is incorrect to attempt to impute it. While dealing with null values is known to be difficult and is already considered among the issues in data cleaning, the needs of responsible data management introduce new problems and much higher stakes of a mistake. Importantly, it's been documented that data quality issues often disproportionately affect members of historically disadvantaged groups. And so we risk compounding technical bias due to data representation with pre-existing bias for members of these groups. Sebastian Shelter and I, together with several of our students, have been building FairPrep, a system that supports data scientists in their day-to-day battles with technical bias. FairPrep helps incorporate new components, such as data pre-processing methods and fairness-enhancing interventions, into complex data science pipelines, and quantifies the effects of these components on multiple objectives, including accuracy and fairness of the classifiers that make part of these pipelines. Our work was motivated in part by serious violations of sound experimental best practices that we found in broadly cited papers and broadly used frameworks for fairness-enhancing interventions. Let us now shift gears and discuss another critical aspect of responsible data management: interpretability. Allowing people to understand the process and the decisions of an ADS. Interpretability is needed because it lets people, including software developers, decision makers, auditors, regulators, individuals who are affected by ADS decisions, and members of the public, exercise agency by accepting or challenging algorithmic decisions, and in the case of decision makers, to take responsibility for these decisions. We have been developing interpretability tools based on the concept of a nutritional label, drawing an analogy to the food industry where simple standard labels convey information about the ingredients and the production process. Short of setting up a chemistry lab, the consumer would otherwise have no access to this information. Similarly, consumers of data products cannot be expected to reproduce the computational procedures just to understand fitness of a dataset for their use. Nutritional labels are designed to support specific decisions rather than provide complete information. For concreteness, let me describe ranking facts, a system that automatically derives nutritional labels for rankings. This system was built by my talented student Kei Yang and is the result of collaboration with Abol Asude, Bill Howe, Jagadish, and Jerome Miklau. Ranking facts is made up of a collection of visual widgets. Each widget addresses an essential aspect of interpretability. The recipe and ingredients widgets help explain the ranking methodology. Recipe succinctly describes the ranking algorithm. For example, for a linear scoring formula, each attribute would be listed together with its weight. Ingredients lists attributes most material to the ranked outcome in order of importance. For example, for a linear model, this list could present the attributes with the highest learned weights. Put another way, the explicit intentions of the designer of the scoring function about which attributes matter and to what extent are stated in the recipe, while ingredients may show attributes that are actually associated with high rank. I already spoke about fairness and diversity, and will not dwell on these properties here. I do, however, want to spend a couple of minutes on an underappreciated aspect of responsibility and of rankings, and that is stability. The stability widget explains whether the ranking methodology is robust on the given dataset. An unstable ranking is one where slight changes to the data, for example, due to uncertainty or noise, or to the methodology, for example, by slightly adjusting the weights in a score-based ranker, could lead to a significant change in the output. This widget can report whether the ranking is sufficiently stable according to some pre-specified criterion, or give a score that indicates the extent of the change required for the ranking to change. My interest in what we are now calling responsible data management started in 2011. That was the year that I subscribed to The New Yorker, and that was also when I read an article by Malcolm Gladwell about the importance of rankings. In his article, he starts by explaining just how arbitrary a ranking can be and how influential, starting with an example of rankings of sports cars, where you can easily get every permutation by suitably changing the scoring formula. And immediately after that, Gladwell dives into the high-stakes game of college rankings. In his article, Gladwell speaks about how values and beliefs can be silently legitimized by technical choices, and about the power that numbers, data, and technology hold in society, setting standards, allowing us to hide behind proxies, and comparing apples and oranges with far-reaching impacts. In a line of work led by the talented Abol Asude, we focused on quantifying and improving the stability of a score-based ranker on a given dataset. The goal is to help a decision maker, such as a human resources manager, to settle on a methodology to rank candidates. The manager has a scoring function in mind. For example, they think that the two numerical scores of an applicant X1 and X2 in the example below should have an equal weight. In addition to staying close to the specified scoring function, allowing X1 and X2 to have almost equal weights in this example, we also incorporate a notion of stability that quantifies whether the output ranking will change due to a small change in attribute weights. This notion of stability is natural for consumers of a ranked list who should be able to assess the magnitude of the region in the weight space that produces the observed ranking. If this region is large, then the same ranked order would be obtained for many choices of weights, and then the ranking is stable. But if the region is small, then we know that only a few weight choices can produce the observed ranking. This may suggest that the ranking was cherry-picked by the producer to obtain a specific outcome and therefore is less trustworthy. Let us now return to our discussion on interpretability, and specifically to the nutritional label metaphor. The data management community has been studying systems and standards for metadata, provenance, and transparency for decades. Responsible development and use of automated decision systems is bringing these favorite topics into the spotlight, but with a twist. To differentiate a nutritional label from more general forms of metadata, Bill Howe and I, in a recent article, articulate several properties. The label should be comprehensible. It is not a complete and therefore overwhelming history of every processing step applied to produce the result. The information on the nutritional label must be short, simple, and clear. The label should be consultative, providing actionable information, not just descriptive metadata. Based on this information, a consumer may cancel unused credit cards to improve their credit score, and a job applicant may take a certification exam to improve their chances of being hired. Labels should also enable comparisons between related products, implying a standard. Finally, they should be composable and computable, derived automatically as data and decisions are produced by the ADS. It is now time to wrap up, and I would like to leave you with a few parting thoughts. In my talk, I gave a perspective on the role that the data management research community can play in the responsible design, development, use, and oversight of automated decision systems, or ADS. I intentionally grounded the discussion in automated hiring tools, a specific use case that gave us ample opportunity to both appreciate the potential benefits of data science and AI in an important domain and to get a sense of the ethical and legal risks. I also intentionally devoted a lot of time to setting the stage, bringing in concepts from law, philosophy, and social science, and grounding them in data management questions before discussing technical research. This breakdown is representative of the work that my students, colleagues, and I have been doing over the past several years. It also underscores that we technologists must think carefully about where in the ADS lifecycle a technical solution is appropriate and where it simply won't do. On a related note, an important thread that runs through our discussion is that we cannot fully automate responsibility. While some of the duties of carrying out the task of, say, legal compliance can in principle be assigned to an algorithm, the accountability for the decisions being made by an ADS always rests with a person. This person may be a decision maker or a regulator, a business leader or a software developer. For this reason, we see our role as researchers in helping build systems that expose the knobs of responsibility to people, for example, in the form of explicit constraints on interpretability mechanisms. We in data management are in a unique position to make an impact. Because data management technology offers a natural centralized point for enforcing policies, we can develop methodologies to transparently and explicitly enforce requirements through the ADS lifecycle. Because of the unique blend of theory and systems in our toolkit, we can help inform regulation by studying the feasible trade-offs between different classes of legal and efficiency requirements. Because of our pragmatic approach, we can support compliance by developing standards for effective and efficient auditing and disclosure, and develop protocols for embedding these standards in systems. To make progress, we may need to step outside our engineering comfort zone and start reasoning in terms of values and beliefs, in addition to checking results against known ground truths and optimizing for efficiency objectives. This seems high risk, but one of the upsides is being able to explain to our children what we do and why it matters. Thank you for your attention. In addition to the first volume of the Data Responsibly comic series that was released today, please also take a look at the Responsible Data Science course that I have been developing and teaching at NYU.